We're going to focus on natural space phenomenon and focus predominantly on black holes. So, what is a black hole? How is it created? And what happens when two black holes circle in on themselves and collide? And in order to understand the collision aspects of it, we'll get into Einstein's theory of general relativity and how do we measure when those black holes actually collide, in which case we use gravitational waves. So let's first start off with what is a black hole?
Space is a pretty dark place. Even so, some areas are darker than others. Nothing is darker than a black hole. A black hole is an area of such immense gravity that nothing, not even light, can escape from it. Black holes form at the end of some stars' lives. The energy that held the star together disappears and it collapses in on itself, producing a magnificent explosion. Here's where things get crazy. All of that material left over from the explosion, many times the mass of our sun, falls into an infinitely small point. Black holes can form in many ways though, and large black holes can have tens to millions of times the mass of our sun trapped in a point smaller than the tip of a pin. Some black holes trap more and more material as their mass increases. The point where all that mass is trapped is called a singularity. It may be infinitely small, but its influence is enormous. Imagine a circle with a singularity in the middle. The gravity on the inside of the circle is so strong that nothing can escape. It sucks in everything, even light. That's why it's black. This circle is known as the event horizon. An event horizon is probably what you are thinking of when you think of a black hole. What would happen, you might wonder, if we took a spacecraft near a black hole's event horizon? The answer? Spaghettification. That's the technical term at least. As our spacecraft approaches, the gravity will be so much stronger on the side closer to the black hole than at the other side that it will get completely stretched out like a piece of spaghetti. Try as you may, you would be hard-pressed to find anything weirder or cooler than a black hole. Presented by NASA's Space Place.
All right, so that's an overview of what is a black hole and why do we care about it. So let's take a look at a situation where we have two black holes that are circling each other, basically going down the drain, and then they collide in on themselves. What happens? How do we measure it? How do we know it really happens? So we use what we call gravitational waves to measure that, but what are gravitational waves? And to understand that, we need to take a step back and take a look at Einstein's theory of general relativity. And to help us with that, Arvin Ash has actually put a great video together that explains what is Einstein's theory of general relativity.
The shortest path between any two distant points on Earth, if you're restricted to the surface of the Earth, is never a straight line because you have to traverse the curvature of Earth. So the shortest path is always curved. So maybe gravity somehow causes a curvature of space itself. He hypothesized that in space, perhaps a straight line is not the shortest path between 2 points, and that perhaps in the presence of mass and energy, space somehow becomes curved, so that the shortest path the light can take is a curved path. This was the key insight that Einstein had about gravity. Einstein's theory was now that gravity was not a force between massive objects, but something that emerges from the interaction of space and massive objects. John Wheeler would later summarize the theory in 12 short words. Space-time tells matter how to move, and matter tells space-time how to curve. That's it. That's general relativity in a nutshell. And orbits of planets could now be explained not by some mysterious force that acts at a distance, but rather an interaction that takes place locally with mass or energy and the space around it. And this can be visually represented by the kind of graphic you see here to show how massive objects like planets form orbits around other massive objects. It's important to note that the trampoline analogy you normally see on TV shows and YouTube videos like this is a 2D plane used for visualization purposes only. The interaction occurs obviously in 3 dimensions, not just 2. It looks more like this graphic. Now this is much more difficult to visualize and animate, so it's typically not used, but it is more accurate. If this is the case, then it means that the speed of light in the presence of gravity will be the same as its speed in empty space. Speed equals distance over time, s equals d over t. But since the distance traveled by the beam of light in a gravitational field is longer due to the curvature of space, in order for the speed of light to remain constant, time itself must pass slower in the gravitational field relative to time in empty space. In other words, time increases proportionately with the curvature of space near the gravitational field compared to empty space to keep the speed of light constant in both reference frames. This is why time is considered distorted by gravity along with space. It is really just part of the same fabric called space-time. This has some massive implications. It implies that the observer experiencing no gravity at all sees the clock in a gravitational field running slower. This means that the clocks on Earth are slightly slower than the clocks on the International Space Station. This effect has been confirmed by many experiments and is taken into account in order to keep the clocks of the GPS satellites in sync with the clocks on Earth. Otherwise, your GPS apps like Google Maps would give you inaccurate locations.
Now that we know that there are ripples in space and we can prove it, what does that look like?
So going back to Einstein's picture, if you think of it in terms of massive bodies affecting the space-time, you can immediately think of a way to communicate information about those bodies from place to place through ripples in space-time.
The waves can be represented by this object I found on a wine bottle, and it's a mesh that you can see, and the waves cause transverse to the direction in which they're moving. They're moving forward, and transverse to that, the space gets tugged like this and collapses like that, tugged like this. And if you look carefully at this, and I'll do this a few times, you'll notice that the little squares in this are exercising a motion where along one direction, it's obvious which direction, I mean the direction I'm pulling in, space is getting expanded, but transverse to that, up and down, space is getting contracted. And that's the key to the whole thing.
LIGO is laid out in an L shape. And each side of the L is 4 kilometers long. 4 kilometers was chosen because the American taxpayers are willing to pay for it, and it's far enough to get an effect that we think we can see. The reason it's an L shape is because gravitational waves cause objects to get closer in one axis and farther in a perpendicular axis, and then vice versa. So we fill the two arms with light from a laser in the corner station, and the light spends about 1/100th of a second in this arm and 1/100th of a second in the other arm, and then the light comes back to the corner station, and the light that spent time in this arm comes back a little bit before or a little bit after the light that spent time in the other arm. And that's how we would detect the effect.
Okay, so those are black holes and how we measure them at a high level. Obviously, you can get much more in depth than that. So let's take a look at some of the other celestial objects that are out there. So first and foremost are quasars. That's obviously one of my favorite. And quasars are a large celestial body that are just all-consuming energy. It's in a massive amount of energy that's compiled into one location. And it's believed by some to have black holes in the center, and it emits a massive amount of energy, basically in a straight line perpendicular to its body. And then there are magnetars. These are known to be the most magnetic stars in the universe. These are ultra-powerful magnetic neutron stars. They're known to erupt pretty much without warning, sometimes lasting hours and months. We know of just shy of a dozen magnetars in the Milky Way galaxy. And then there are pulsars, which are thought to be rapidly rotating neutron stars that emits regular pulses of radio waves and other electromagnetic radiation at rates up to 1,000 pulses per second. And the last phenomenon that I want to talk about is when a star goes supernova. And I don't mean supernova like the Marvel character. When a star goes supernova, it basically collapses or explodes in a matter of a couple seconds. And there's really two thoughts to why this could happen. The first one is whenever a star collapses in upon itself. So with massive stars burning huge amounts of energy at their cores or centers, this produces tons of energy. So the center gets very hot. Heat generates pressure, and the pressure created by the star's nuclear burning also keeps that star from collapsing. A star is balanced between two opposite forces. The star's gravity tries to pull and squeeze the star into its smallest, tightest ball possible, but the nuclear fuel burning at the star's core creates strong outward pressure. This pressure pushes and resists the inward squeeze of gravity. When a massive star runs out of fuel, it cools off. This causes the pressure to drop. Gravity in this case wins out and the star suddenly collapses in a matter of even up to 15 seconds. The collapse happens so quickly that it creates enormous shock waves that cause the outer part of the star to explode. Usually a very dense core is left behind, along with an expanding cloud of hot gas called a nebula, which if you take a look at the Hubble photographs, you can see lots of great nebulas. A supernova is a star that's about 10 times the size of our sun, might leave behind dense objects, and those dense objects are what we call black holes. The second type of supernova can happen in systems where two stars are orbiting one another, and at least one of those stars is an Earth-sized white dwarf. A white dwarf is what's left behind after a star the size of our sun has run out of fuel. If one white dwarf collides with another, it pulls too much matter from its nearby star, and the white dwarf can collapse and explode.